Okay, so Assalamualaikum and a very good afternoon. I would like to say to Dr. Robert, my name is Adam Syukran Bimam Azahari, and today I'll be starting off our presentation for Real-Time Systems Assignment 2. So next slide. Okay, so firstly, I'll be giving a brief introduction regarding the two different types of deadlines that can exist. Firstly is that we have hard deadlines, or in such a system where in a real-time system, if the output or the result of an operation comes after the deadline, and for hard deadlines, this makes it so that it no longer has any utility. So we can see that in real-time system, the deadline is very important, especially when you have things like hard deadlines. And in a different system or something like a safety critical system, not only does the result no longer have any utility if it passes the deadline, but it can also cause damage to the system in a lot of like very time-focused scenarios, like let's say in an air traffic control system. So now that we have an idea of like about deadlines, let's see how that applies to our particular paper. So next slide. So for our team we studied a paper called a real-time precision agriculture monitoring system using mobile sync in WSN. Those are the author's names. It was written in 2018. So it has two different types of real-time systems. So a brief description regarding the two of them is that for hard real-time systems where the result needs to be done in a timely manner. So what this means is that if the result of the operation comes too late, then it can essentially cause a system failure, or it can cause a great detriment to the entire system. So that's more related to like the hard deadline that I've discussed in the previous slide. So that's what hard real-time system is. For the soft real-time system is that if the result is a little bit late and not in a timely manner, it does still have some utility and the system will not suffer from a catastrophic failure. So that's the difference between a hard real-time system and a soft real-time system. So for our particular paper that we studied, this paper is basically talking about how sensors can be applied to a particular agricultural field and how it can help to better optimize watering, and also help to like monitor the different attributes that you would normally want to see in an agricultural field, like let's say humidity, moisture, sun, etc., etc. So with regards to our particular paper or our particular project that we studied, is the type of system is going to be a soft real-time system, because even if the sensors were late by a few seconds or a few minutes, it will not cause a catastrophic failure for the system. So that's why we would like to categorize this particular paper as a soft real-time system. So in terms of response time frames, if we would like to highlight two different ones, which is periodic and aperiodic stimuli that you can look at. So periodic stimuli is something that you would normally see over a certain time period. This can be attributed to the mobile sync in our particular paper, whereby that just a little bit of brief rundown of how it works is that if a mobile sync or like a tractor passes through a certain area, then the sensors in that particular area will send the data to that mobile sync. So that's how that works. So we would like to classify that as periodic stimuli, and aperiodic stimuli is something that is like continuously being looked at. So we can say that that is more related to like the water systems or the water sensors in that particular system. So we would like to make or divide it into two different types of time frames, which is real time and also dependent on external factors or environmental factors. So in terms of real time, according to the authors, they hooked up a water sensor and they hooked it up to a water pump. So if the moisture level or the water level of the soil is too low, then it will automatically turn on the water pumps. So that's how that works. And in terms of depending on external factors or environmental factors, this one would be regarding the mobile sync or the tractor, whereby that if it reaches a certain range to the sensors, then only it will send that data. So that's what I would like to classify, or that's what we would like to classify as dependent on external factors. So with that, I would like to pass it to my colleague. Thank you very much.
Okay, so talking about the system design, so basically everything that Adam mentioned involves in the system design. So it basically involves the combination of both hardware and software to basically monitor the agriculture field and basically optimize the irrigation practices. So this figure just illustrates a simple illustration of how the whole system works. So obviously the sensors are involved here, which is temperature, humidity, as well as soil moisture levels. Sensors are basically arranged in a grid-like layout. So once the data is collected from this sensors, it will go to a Node MCU board, which stores it, and that board itself is connected to a Wi-Fi and a Bluetooth, which will wirelessly send the collected data to a centralized location for further analysis and visualization. So underneath the system design, we have the hardware design. So obviously the hardware components that are involved in this system is Node MCU board, the temperature, humidity, and soil moisture sensors, a smartphone, as well as a Wi-Fi and a Bluetooth model, and a general purpose agricultural vehicle, which is the mobile sync. So, and how these hardwares are connected, the sensors are connected to the Node MCU using GPIO pins, and the node itself is the Node MCU board. It's connected to the Wi-Fi and the Bluetooth, which later will transmit wirelessly to the central location. And then the mobile sync is equipped with the Wi-Fi or Bluetooth module, which will receive that data from the board. And then later on, the smartphone is used for the interface of the system. So that's why we have the software design. So the software design composes of two components, which is the firmware of the Node MCU board as well as the mobile application. So as mentioned before, a Node MCU board will collect the data from the sensors and send it wirelessly to the central location, so it can be analyzed statistically and using machine learning methods. So then comes the mobile application. So all the data that's gathered from the board, it will be inputted in a mobile application in an interface. So it will provide users with real-time access to the data collected by the system and enables remote control of the system, such as turning on and off the water pump based on the data gathered. So therefore, these systems help farmers to monitor their agriculture field in real time. So that's about it for the system design.
Okay, hi, madam. My name is Zaidhaan, and I'll be talking about the task scheduling process. So first, I'll go over the basic tasks that occur in the system. So firstly will be the data collection. So as mentioned by my colleagues previously, the data is going to be collected from sensors and they're going to be inputted into a bunch of nodes, MCUs, that are nodes within a square grid. So these sensors will be collecting data such as moisture levels, temperature, humidity, and things like that. So that's like the first step in the whole process. The next step would be to transmit this data to the mobile sync. So the mobile sync will be a tractor that's going to be walking around the field and going near each sensor to collect their readings. So the reason why it's called a sync is because if you imagine a sync, it takes in a bunch of data and then it concentrates it into one point. So in this case, the tractor is going to be the sync and it's going to receive data from a bunch of sensor nodes that are nearby it. And so the mobile sync, it'll be walking around in a predetermined path, which makes sure that it touches all the sensors in its path. So once it goes through the path, it will be getting data from all the nodes, which will be connected to a bunch of sensors that are taking all their readings. And then the data on the mobile sync, it will need to be pre-processed. The reason why it needs to be pre-processed is because initially the raw sensor data is going to be very dense and it's going to have a lot of unnecessary information. And so to reduce the bandwidth, because the data, it needs to be sent to a cloud service, it needs to be sent to a third-party service to be analyzed. So you don't want to send too much data through that. So you want to pre-process it so that you can reduce the bandwidth requirements for it, and you can also improve the overall efficiency of the system. So that's the third step in the process. And then the fourth would be to actually visualize the data, because in reality, the system that the authors described in their paper, it doesn't directly control any of the water pumps or anything like that, but rather it just provides a visualization so that it's easier for farmers and to better understand how to actually respond to these environmental conditions. So basically, Just what I described so far, these are all the processes that occur throughout this whole system. So the data collection, the transmission, and the pre-processing, as well as the visualization, they'll be all happening when the sensor nodes are close to the mobile sync. Then it will be happening in real time. So when the mobile sync moves away from a sensor, and then it pretty much becomes inactive. So next, we can move on to the next slide to discuss the multitasking application method of this. So there is no method that has been explicitly mentioned in the paper, but we can infer by looking at the paper that it follows the model of concurrent data processing. So what this means is that all the tasks that are happening, they're happening at the same time, at least in the real-time time frame. So as mentioned previously, the process consists of collecting, transmitting, pre-processing, visualizing, as well as updating the data that's done all concurrently. So when the mobile node is within close vicinity of a sensor, then it's going to be sending the data, and at the same time, the mobile node will be ingesting the data. It will be pre-processing it, and it will be also sending the data to be visualized all in a single pipeline. So if instead you were to do this in a batch process, then that would result in significant delays, because you need to wait for like a batch of sensor data to be prepared, and then you need to send that batch at once, and then you need to process it, and then you have to do it all in sequence, and that will cause a few delays. So doing this in real time allows the farmers to have the most up-to-date information. So with that, I'll pass it off to Dhinesshah.
Okay, all right. My name is Dhinesshah, and now I will be explaining about process development and deployment of a real-time agriculture monitoring system, and in this case, using a mobile sync in wireless sensor networks. So the first is the design. The system in the study was designed to monitor several environment characteristics such as the temperature, humidity, soil moisture, and light intensity using numerous sensors. And the system was also intended to give real-time crop growth monitoring and detection of any irregularities. Next, the system's hardware selection. It is chosen for their low power consumption, small form factor, and compliance with the WSN architecture, followed by the software development. In this case, it is not mentioned in this specific study, but for operating systems, Contiki can be utilized in this kind of scenario. Next is deployment. The system is then deployed in a farm to test its performance in a real-world setting. The sensor nodes are distributed in different parts of the farm, and the mobile sync is then programmed to collect the data periodically from the sensor nodes. And in this study, the sensor node deployment strategy consists of two steps, which is one, the coordinates finding, and second is the path planning. And the strategies are deployed for covering the agricultural field without leaving any blind spots behind. Then the data collected is evaluated to track the environmental conditions and crop growth under the data analysis. And finally, the system can be evaluated based on several performance, such as energy efficiency, packet delivery ratio, and delay. Moving on to the next slide. Okay, so for the operating system used, it is not mentioned in this study. However, the system is built with wireless sensor network, as mentioned, and a mobile sync for data collection. The operation system is mostly likely an embedded operating system developed for a low power and resource constrained device like WSNs. Also not to forget that the authors have mentioned that Node MCU is used to develop the system prototype. So this means that there is no operating system required, because the Node MCU itself make use of the expressive non-OS SDK. So a Wi-Fi connection can be made with a few lines of code, and input-output pins can be defined according to one's needs, transforming it into a IoT tool required for the system. So in general, the choice of operating system for a smart agriculture monitoring system is determined by the system-specific requirements. Because of the minimal memory footprint and efficient resource consumption, embedded operating systems such as FreeRTOS, TinyOS, and Contiki are often used in such a scenario. Moving on to next slide. So here we will discuss about the input and output approach of this study. So for input, we have sensor data. So the system gathers information from numerous sensors installed in the agricultural field, such as temperature, humidity, light intensity, soil moisture, and pH level. The sensors are linked to the Node MCU microcontroller, which reads the data and wirelessly transfer it to the base station. Next, for the input is the user input. So basically, a farmer can enter information such as crop kind, irrigation schedule, and fertilization strategy into the system. The data is utilized to optimize system performance and deliver tailored feedback to the farmer in real time. And for output, we have database. The system saves all the collected data in the database, which the farmer or agriculture expert can access for analysis and decision making. The database contains both historical and real-time data, allowing for trend analysis and predictions. Next will be the mobile sync. So for mobile sync, the system employs a mobile sync, which is a movable device that goes around the entire agricultural field, collecting data from all the sensor nodes. The data will be then wirelessly received by the mobile sync and processed in real time. And it also does data analysis on the received data by implementing machine learning techniques to detect any anomalies. And finally, for the alerts, when the sensor data indicates a certain environmental condition that are beyond the required range, the system sends a real-time alarm to the farmer or the agricultural expert, and it enables the farmer to take prompt actions to protect the crops. So now I will pass to the next presenter.
Okay, so now the significance of the system. So the first benefit is we have that this kind of system helps farmers to monitor environmental conditions such as the temperature and humidity, and providing them with the early warning. So that's why it prompts an action to prevent, mitigate and the impact of these outbreaks, and reducing the crop losses as well as improving the overall yields, and this all helps for the farmers. And the second benefit is the system provides an accurate and convenient way for the farmers to collect data on their water usage as well as the nutrient rates, which can help to comply with the regulatory requirements, and this reduces administrative burden on farmers as well as helps them to avoid penalties and for non-compliance. And then the other benefit is that the system helps improve food security as well as reduces waste by optimizing the production practices. And the other benefit is the system provides weather data that can help farmers plan their harvest schedules and irrigation systems more effectively, so reducing water waste as well as increasing crop yields, and can also help farmers reduce the dependence on synthetic fertilizers, which comes to the last benefit is that it reduces the use of fertilizers and pesticides, so it's more healthier towards the environment, so it reduces greenhouse emissions, which helps to mitigate the climate change. So that's it for the significance.
Thank you all for our presentation. Thank you very much.